to this sixth webinar of IST. It's my indeed great pleasure to introduce today's speaker, Dr. C.M. Kishtawal. He's a farmer scientist and group director at Space Application Center. Received his master degree in physics with a specialization in astrophysics from Kumail University, Nainital in 1983. He joined ISRO in 1984 and completed his PhD from IIT Delhi in 1994. His research area include the development of techniques for operational prediction of tropical cyclone using satellite observation, monsoon prediction, operational retrieval of cloud motion winds from satellite observation, and impact of land surface process on weather and climate, particularly the impact of cultural intensification and urbanization. During 1998 to 1999, he was research associate at Florida State University, and he worked there towards the development of multimodal ensemble technique for improvement of weather prediction on medium range to seasonal time scales. During 2009 to 10, he was a visiting scientist at Purdue University, West Lafayette, US, where he worked on observational and theoretical aspects of land surface atmospheric interaction process. He has around 170 peer-reviewed research publication in various scientific journals. So I request Kishtawal sir to deliver the webinar. Over to you, sir.
Thank you so much. Thank you so much, Dr. Sinha. So first of all, I must thank you and Dr. Chandrasekhar for giving me this opportunity. This is a wonderful opportunity for me to talk to the younger generation, and I heartily welcome everybody and all the students. So please feel free to ask any question. You can take the questions at the end of this talk. So my today's talk is applications of satellite observations for numerical weather prediction. So I'll be talking for about 1 hour on this topic. So I hope you'll enjoy my talk. So basically, what is weather forecasting? Basically, weather forecasting is a prediction of the state of the atmosphere for the future time and for a given location. So now what is the definition of future as far as the weather prediction is concerned? So what are different terms of the future? So when we predict for a few hours in advance, like 1 hour, 2 hours in advance, so that's called the nowcasting. For 1 to 15 days, it is called weather forecasting. Basically, the medium range of weather forecasting, but in general, it is called weather forecasting. And from 15 to 30 days or even 40 days, it is called the sub-season to sub-season, S to S forecast. And this is very popular these days because there's a lot of emphasis and this is a gap area. So there's a lot of big things can happen in this time range of the prediction, and a lot of research is going on. Then we come to the next time scale, that is 1 to 12 months, and that is called the seasonal forecasting. And then there is another class of the forecast that is called 1 to 100 years. So that you must have heard that people are talking about what will happen after 50 years or after 70 years, some glacier will melt and all this kind of things you must be hearing. So that is also done by the kind of forecasting that is called the climate forecasting. So there are different ways and different methods. There are same models, but there are different processes that govern the forecast at different time scales. And you all know that how the weather forecasting is used. So people use weather forecasting nowadays for various applications, many things. I think nowadays there is not a single area which do not use weather forecasting. Right from the cricket match, they are very much dependent on forecasting because the public and the response and the pitch, etc., that depends upon the condition of weather. Then tourism, like for example, nowadays there is a snowfall season, so people visit the snowfall areas and they enjoy, and then it depends on when the snow will fall. So a lot of people are interested in knowing that when the snowfall will take place, particularly in the tourism industry. Agriculture, of course, a huge beneficiary of the weather forecasting. Aviation, I think the story of weather forecasting will not be complete. Aviation sector, the airline sector is the biggest user of the weather forecasting services because their flight operations, landing, taking off, all depends upon the weather forecasting. Nowadays, there is a lot of fog situation is taking place in the Delhi, and lots of flights are getting delayed or rescheduled because of that. And it is a very expensive to reschedule a flight and handle this congestion of the traffic and the transporters and the travelers. So there's a lot of meaning of weather forecasting for that. Tropical cyclone forecasting, you can see that. So nowadays, the markets, the malls and supermarkets, they depend a lot on the weather forecasting. For example, you are in the rainy season or for maybe in the winter season. And if you know that the next two weeks, there is going to be very, very cold. So a lot of supermarkets and the malls will store the jackets and that kind of sweaters and the mufflers. And if they store all those things and the cold does not happen, then all these things will go waste. And they will lose a lot of money on that. So they should know exactly then what is going to be the weather in the next couple of days or couple of weeks for their sales and operations. Then in the naval operations, ships, etc., there is a lot of utilization of weather forecasting. So I think there are many people. I cannot imagine that what kind of people are using the weather forecasting these days. So nowadays, what happens that weather and forecasting mostly is handled by weather and climate models. So what is a climate model and weather prediction model? Actually, this weather prediction model is a software kind of thing. So this software contains all the laws of physics and the thermodynamics and the motion. So basically the Newton's laws of motion, laws of thermodynamics, energy, etc. All these things are embedded into the equations. And these equations are solved by very powerful computers, because nowadays people are going to the very high resolution models, like they are predicting global fields at 9-kilometer resolution, which is extremely high resolution. And it means you are handling billions of operations at one point of time, billions of operations per second, billions of mathematical calculations per second. So it requires huge computers. So these kind of calculations are done over the grid, which is shown in this picture. And they also have a vertical structure. So it is not only up to the surface, they are also dealing with the vertical structure of the atmosphere. They go up to 50, 100 kilometers, and also in the deeper soil layers and deeper ocean layers. And all these things are governed by different equations. So all these equations are to be solved. And that is why this the modern day weather forecasting is operated. So basically the numerical weather prediction in this particular, when I'm talking about the model-based numerical weather prediction, is highly sensitive to the initial condition. So if you have better initial conditions, you have a good observation, you have a better initial condition. And if you have a better initial condition, you have a better forecast. So everything actually starts from a good observation. So observation is extremely important. So why is observation is important? I'm going to discuss few slides on that. So now the question comes that how the quality of the observations affect our ability to predict the weather. And the second question related is that why we can't predict the weather accurately beyond few days. So as this graph shows that the weather prediction essentially skill of the weather prediction goes to zero after 2 weeks. So 2 weeks I'm telling on a very, I think very generous estimate. Normally it is not 2 weeks, it is few days only. After 6-7 days in the tropics, but in the tropical country like India, this skill goes down very rapidly. So beyond that, we don't have a skill. So what I'm saying, the zero skill means after a few days, the prediction errors of these models is not better than the climatology. So we can get the same thing from the climatology. Everybody knows that the January, there will be cold. Everybody knows that the monsoon, it will be rain. So the error of this guess is not better than a common man can know. So that is when we say that the prediction skill has gone down. So what is the main reason for that? The main reason is basically the non-linearity. What is non-linearity? Because there are so many equations in the model and many terms are non-linear. So I'll explain what is non-linear. And this non-linearity is one big culprit, or maybe the big phenomena behind our limitation of the ability to predict the weather too much. We cannot go up to 1 month in the weather forecasting. why we cannot go. One reason is nonlinearity. So now, this is a very simple nonlinear model actually. Second term is actually x square. The 2 is misplaced in this slide. But the equation is a very simple nonlinear model. Very simple. Anybody can write it if somebody knows a very little bit of programming. So x n plus 1 time step is equal to x n square minus 2xn. So that is a very simple model. I think it cannot be more simple than that. It's a very simple model. So I did it myself actually on a small computer. So next step of the x is the previous step is square minus 2 of the previous square. That's it. It's simple nonlinear model. Now there are two values. One is the blue color and one is the red color. So blue, I cannot see the blue color value. It is 2.345 maybe. 2.345. So that is, let us assume that is observation. And if you slightly deviate this initial value, starting value, and we make it 2.451 or 2.345, 2.346. Okay. Just I made a small change in the third decimal place. And you see what happened to the outcome. So after 10th time step, these two things are not matching when they started from a very close initial condition. Okay, so the error was in the last third decimal place only. And it made a huge difference after maybe 8th time step, they are not matching at all. So that is and what is the nonlinear term in this? The nonlinear term is x square, because they are multiplying. So x and xn is not the nonlinear term. X square is the nonlinear term. So x square is playing the big problem here, and after 8th time step, you are not able to differentiate, and it is completely random. They are not able to match. Now let us repeat the same experiment, and this time I've taken this black thing also, and I have made the error in the 4th decimal place. So it is 2.3451. So I'm going into the 4th decimal place. So you can see that by improving my forecast, this black line, this thin black line is going slightly, it is matching up to maybe 15 time steps. But after that, again, they are going beyond. We don't have any control on that. It is out of there is no correlation between two measurements after 10th or 15th time steps. So what happens is that a small error, as small as the 4th decimal place, can make such a big difference because we are not able to predict this system after 15 time steps. So this is happening because of nonlinearity. Small errors grow in time, and then they become a big error, and then everything goes out of control. And just this is, I'm not trying to frighten you from these equations, but you know that in the model contains several such equations, and there are nonlinearity everywhere. So small error in the initial conditions can make a large difference in the final condition. So that is called the butterfly effect. Why it is called butterfly effect? Because of two reasons. Number one, it means that a small change like a flap of a butterfly is how much? It contains very small energy, can create a large difference like a tornado. So somewhere in the world, a butterfly flaps his wings, and then it can create a tornado somewhere. That is the symbolic reference to this picture in the above. And in the second picture, you can see it is an actual diagram of a Lorentz diagram, and then it means that you can see there are two small dots I have made in the first place. At time t equal to 0, there are 2 points which are very close together. But after maybe 1,000 time steps, if I run this model, then they are very diametrically opposite, and they are very much far apart from each other. So very small change. So sensitive dependency to the initial condition. That is called the chaos. And in the mathematical terms, it is called the nonlinearity and the chaos. So this is a very important phenomena and very important concept in the how we define the predictability, how much we can predict. And we can never get so close to each other. The observations cannot be so accurate that they cannot have a small error of the 10 to the minus 15 or 10 to the minus 20. That kind of error we cannot have, at least in the next 20, 30 years. So even if we have, then also we cannot predict it, because these nonlinear terms are really problem. And you know, there was a movie called the Butterfly Effect, and that is also on a similar concept. Actually, it was a blockbuster hit movie. It was made on the budget of $13 million and it grossed $100 million. And this movie also is in this movie, actually, there is a boy who can go back into the time and change his past. But what happens in the future is not on his control. The things go in such a way that he might not have he had not imagined those things. So in the similar lines, these people made another movies, the part 2 and part 3, but those were very big disasters in the box office. So that itself, they did not assume the outcome of those 2 sequels of this movie. So that itself became a victim of this kind of butterfly effect. And actually, in the butterfly effect of the chaos can become very complex as the dimensions increase. So what I showed you the example was a 2-dimensional projection of that things. But actual situation, the butterfly effect can be very, very complex, particularly in the weather models. So what are the other sources of error? Basically, the initial condition I told you, physics errors are very important because most of the physics in the models is parameterized. So what is parameterized means it is not represented in terms of the prognostic equations. Actually, we have a parameterized physics in that, like the radiation, friction, dissipation, diffusion, etc. These terms are parameterized. Many times the many convective processes are parameterized. So these parameterization, this physics, our understanding of physics is not very perfect. How very many crowd droplets will grow into a drop, we don't know very precisely about that, and what conditions, how it will happen, how the diffusion will take place, how the radiation will interact with different parts of the aerosols. These things we know very precisely, but that is not precise enough to not cause a source of error. Then there are in the errors in the numerical approximation, because actual equations of the physics are differential equations. But what we use in the models is not the differential equations. It's not exactly differential equations, but they are difference equations, like the finite difference equation or the central difference, numerical difference, like the finite element methods, and they are approximations of the differential equations. So that approximation also leads to some errors. Then we have the lower boundary condition errors, like the vegetation snow. Also, our understanding, our measurements of these are never perfect, because no measurement in this world is perfect. No measurement is perfect. Please note that down. Always we make the observation or any measurement with certain amount of uncertainty. So there is no measurement without uncertainty. So this is the physics parameterization. There are different ways of parameterization. So they are all subjected to error actually, and then they contribute to the error in the forecasting. And that is why our forecasts are not skillful beyond a certain amount of time. This is the numerical procedure. As I told you, that how you can see that how the df by dx in the last, you see the last equation, df by dx is approximated by f x plus delta x minus f x minus delta x divided by 2 delta x. So from dx, we have gone to delta x. Dx is 10 to 0. Basically, dx is infinitely small in the differential equation. But delta x is not as infinitely small. It is had its finite value. So the difference between the infinitely small value and the finite value, measurable value, is that what is causing the difference between the forecast. So I am sorry, I'm not using many equations. That's my last equation in this whole PPT. Okay. So now, so what is the conclusion of this picture is that the observations are extremely important, particularly this slide, that even if you make a small improvement in the observations, our forecasts are going to change very drastically. Sorry. I have used many animations in that. So observations are very critical. So this talk is mostly focused on the observations. So we make observations of many parameters, and I've called this the observation of the Earth system. So Earth system is a system of systems. There are many systems within the Earth system. So there is the atmosphere, there is a hydrosphere, what is made of water, the water vapor, transport, evaporation, precipitation, like that. Then we have a cryosphere, which is made of the ice. We have a biosphere. Biosphere is a very important parameter. It's a very important process. When monsoon takes place, when there is a rain, suddenly the vegetation grows, and it changes the complete radiation balance of the atmosphere. So it interacts with the radiation in a very different way than a bare earth will. So it is a very important thing, and people are still trying to understand how this biosphere actually contributes to the our predictability. And then geosphere. You will be surprised that even geosphere plays a very, very important role in defining how the weather prediction goes. Suppose there is a volcanic eruption takes place somewhere, and there's a lot of dust and a lot of volcanic ash is there. It will completely change the radiation, and even it will change the clouds. It will change the precipitation processes. It will change everything. So geosphere is also a very big part of the atmosphere, atmospheric Earth system. So we have to understand, we have to observe each and everything. Of course, I'm not talking about geosphere and biosphere in this thing. I'm talking about only atmosphere. So we have to take the precise measurement of the atmosphere. And this, if you see the animation on the right-hand side, it is the water vapor transport. And you can see that the water vapor changes at a certain place like the Amazon forest can affect, they get initiated in the Amazon forest, and then after that they get transported to a very far off like Europe. So the processes in the Amazon forest can affect the weather in the Europe after some time. In fact, they can affect the weather in India also. And then, but that is a matter of further research. So what kind of measurements we are taking? So there are some conventional measurements like the automatic weather stations. So, you know, this is what a automated weather station looks like, AWS. And there are many, I think there are lots of private companies are installing their observatories, and they're very small in size. And nowadays, they are not even this big. They are as small as a small box, and anybody can install them. So they provide you the measurements at the surface level. So they provide the wind speed, temperature, humidity, surface pressure, all these things. And it's a very important source of measurement. And you know how much they are? They are approximately 10,000 official stations, and maybe 20-30,000 private stations. So total maybe 40,000 stations are there across the world. But you know, as you know, that there are so many places where these observations are not available. For example, oceans. You see the oceans, these weather observations are not available. There are a lot of places in the African regions, like the third world countries, and a lot of deserts, African deserts, they're not available because it is very difficult to maintain and install observatories over that regions and get the collect and maintain them. If some instrument and some sensor goes wrong, it is very difficult to go there and replace that sensor. So that is why you can see in the Greenland, there are very few observations. If you see the Antarctica, so the density of the observations is not so high. Europe, you see very good density. In America, it is very good density. India, China also very, very nice. But you can see some other countries are not so good in coverage. This one issue is the maintenance of these observations, these AWS networks. You can see that sometimes if they're in the poor condition, they can give wrong observations. And ultimately that goes as some model can take it as a real observation, and then there are a lot of anomalies. So on the right hand side, you can see there's an anomaly, which was a false anomaly, just coming because of the a faulty weather station. Then a very important observation is the upper air observation. And upper air observations are taken by the flying balloons, mostly twice a day, but at least once a day. So they gives you a lot of good measurements like the temperature profiles, the humidity profiles, wind profiles. And let me tell you, this is a very important source of observations. Without that, we cannot predict weather accurately at all. Surface measurements are not enough to tell you that what the weather is going to look like. You have to understand the three-dimensional structure of the weather, and these are one of the very important sources of the information. And they are approximately 1,000 to 1,500 upper air observations, because you know they're expensive. You have to maintain a balloon laboratory. You have to fill the balloon. You require a manpower to handle that. They are not automated, and they are still manually done. So somebody has to there and go and fill the balloon and then launch the balloon and note the recording. So many countries cannot even afford this kind of operations. So there are not many. There are only 1,000 to cover the entire globe. And this is one of the very important sources of observation. So 1,000 observatories like that. And again, we don't have these observations over the oceans and over the Arctic or the Antarctic or the desert regions. That is the problem. Over the oceans also, we have the in-situ buoys, Argos buoys. So much things are covered. There are approximately 2,000 such observatories are there over the entire ocean. But again, the problem is that you have to maintain them. And if something goes wrong, you have to go physically there and you have to correct it. So, which is a very costly operation. So these are the numbers. How much? I think they are 1 lakh surface observation. Then there are upper air, I think 1100. There are 2100 buoys or measurements. Aircraft measurements are, I think, around 200,000. Pilot balloons are approximately 1,700. So this is the sea, and then you can clearly see the gaps over the oceans and the and other parts of the land. So what is the need? So we need a platform where we can measure the globe more continuously and more frequently. So satellite comes into our mind that satellite is one platform which has the capability to measure the globe entirely and with a lot of high repeativity and larger coverage. So what is the advantage of the satellite observation is that they provide you very huge coverage. They have a better repeativity. So they come sometimes many of the satellites have a repeativity of 15 minutes or maybe 10 minutes. So after every 10 minutes, the geostationary satellites can provide you measurements. They are representative. The representative means there is a single instrument which is measuring the entire globe. So if you see the polar orbiting satellite, it is one instrument only. So if something goes wrong, we have to correct that instrument only. We don't have to go to every place and then correct it. We have to correct only one instrument, which is on the satellite. So we have to correct from software or on the ground, whatever we correct. So we have to correct only one time, and then everything will be corrected. So that is called the representative observations. So these are the history of this weather observations. Initially, there are some black and white pictures taken by the analog. So there are not even digital pictures at that time, but at least they gave us, it started in April 1, 1960. And after that, there was no looking back. So the weather forecasting satellites have made a big history after that. So after these initial pictures, but these initial pictures told us that the Earth is a whole single system. And we cannot say that it is Indian weather or it is a maybe American weather or Russian weather. It's not like that. The weather is same. It is encompassing the entire Earth. So what is happening today in maybe Africa, today it can travel to America, to India, and then it can affect your weather. So you have to observe the whole Earth to be able to predict the weather. And for the last last many years, the satellite observations have made a big progress. Initially, they were just like analog pictures, and now they have come to the hyperspectral, multispectral, multi-channels, and all these things. So today we are talking about the I think many thousand channels of the observations we are taking from single satellites, and they are providing us the very valuable measurements. So, and the resolutions have also increased. Now we are talking about the GPS and the laser-based systems. So satellite observations have come a long way actually. Nowadays, the advanced weather satellite looks like this. They have a very advanced sensors like the extreme ultraviolet X-ray radiometers, space environment in-situ observations, magnetometers, advanced baseline imagers, geostationary lightning. They can measure the lightning also. They can measure the solar ultraviolet radiation. So they can measure everything. And they are advanced sensors. And India is also going in 2025 with this kind of systems. And we have many such satellites circling the Earth. There are approximately 100 weather satellites in the orbit right now. And they provide the very valuable measurements for the forecasting and weather observations. And the satellites come in the various sizes. People are nowadays talking about the very small size satellites. For example, CubeSats, which are hardly 5 kilograms, 5 kilogram satellites. But what is the advantage that the polar orbiting satellites, they come only once or twice a day on a certain place. So one satellite can cover one location maximum twice, 2 times a day. But if we have many such satellites, like 100 satellites like that, so we can guarantee that every spot will be covered every half an hour, just like GPS. So they measure from 5 kilogram to approximately 2,000 kilograms. So the heaviest satellites are approximately 7,000, maybe 7,000 pounds, or maybe 3,000 kilograms. Like the most geostationary satellites are approximately this weight. So it is of the weight of a small truck. So this is a geostationary satellite. So basically the geostationary does it revolves with the same speed of rotation as the Earth rotates on its axis. So relatively for this satellite, the Earth looks stationary. So that's why it's called the geostationary satellite. So they are above 36,000 kilometers approximately. So 36,000 kilometers is a very huge distance. So from that distance, the clarity of the images is not so sharp as you can get from the, suppose the satellite is at few hundred kilometers. So, but the advantage is that they can take the repeated measurements. So this kind of measurement they can take. So in this, the Earth is not moving, only the cloud system is moving. So because the satellite is also moving with the same speed as Earth, so it is measuring only clouds. And these, they can measure the clouds at every 15-minute time interval, so which is a very high repeativity for any observation. And they give you very valuable measurements like the wind, and they give you sea surface temperature, fog, so many kind of parameters. They give you aerosols, they can give you rainfall, so many parameters. And I think there are more than 35 parameters which are coming from present INSAT geostationary satellite of India. And there are many geostationary satellites around the world, and the polar satellites which are dedicated to the weather services. And these are the names of that. You can see our INSAT 3D also in this list. And there are GOES satellites, which are American satellites. There are Meteosat, European. Then there are Himawari by Japan. Then there are FY series of satellites by Chinese. And there are Korean satellites. There are many satellites, Russian satellites, and there are so many constellation satellites. So this is basically all the geostationary satellites are placed in the equatorial plane, and they revolve with the same speed as the Earth rotates. And this is a list of geostationary satellites which were launched by India. So India has a very rich history of geostationary satellites. And currently also there are 2 geostationary satellites in the orbit, INSAT 3D and 3DR. So satellites basically take measurements in the ultraviolet, not in the ultraviolet, sorry. They take visible, infrared, and microwave. They are the 3 preferred spectrum of the preferred frequencies on which the weather satellites make measurements. They don't use ultraviolet or the long wave radiations. They mostly rely on visible, infrared, and microwave. They have their own limitations and their qualities, which I'm not going too much into that detail. So these satellites come into, and these sensors come into active and passive. Active sensors, they use their own source of illuminations, while passive sensors rely on the emitted radiations, which is emitted or the reflected from the Earth's surface. And there are a number of parameters, as I told you: sea surface temperature, water profiles, temperature profiles, and the sea surface height, rainfall, precipitation, all these parameters. I think there are hundreds of parameters which are made available by these satellites. And all these satellites observations mostly go into the models for better prediction. Nowadays, a different class of satellite observations are coming, and they're becoming hugely popular because of their accuracy and their demand. One is coming from the GPS satellites. The GPS satellite was basically not designed to measure the weather parameters, but later on people found that they are extremely useful tool for predicting the weather, the upper structure of the atmosphere. Actually, whenever the GPS satellite sends a signal, it goes to your mobile or maybe some other satellite. That is called the low orbiting satellites. And when it goes to the low orbiting satellite, actually it has to pass through the atmosphere. And this signal actually bends. So how much it bends, it gives a lot of information about the atmosphere structure of the temperature and humidity. And no other satellite can give you the so much precise measurements of the vertical structure of the atmosphere as the GPS satellites. And people are thinking of launching hundreds of such satellites so that they can get very repeated observations of this type. And these observations has made a huge impact on the weather forecasting. These kind of observations they give a lot of benefit to the weather forecasting. Weather forecasting improves if you put this kind of observations into the model. Then another class of satellite is the GPS reflectometry. So earlier you were taking about the direct signal which was passing through the atmosphere. Now it is a reflected signal. So GPS signal also goes to the ocean. It gets reflected from that. It again passes through the atmosphere and goes to the satellite. So this reflected signal actually tells you a lot about the wind structure of the atmosphere. Because the winds affect the ocean floor, and ocean floor becomes rough if the winds are very high. You can see on the right hand side the scatter plot that these observations are extremely accurate. Actually, they are very accurate and they have a very big range. They can provide the measurements of the tropical cyclones where the wind speeds are very high. And normally a normal typical microwave sensor like the scatterometer will not give you the wind speed beyond 25, 26 meters per second. But these sensors, like because they are working in the L band frequencies, which are very long wavelength, so they are not affected by the rainfall or the clouds, or not even by the rainfall. So they are very valuable for measuring the rainfall and or the wind speed in the tropical cyclone situation where the rainfall is very high. So as I told you that these measurements are not affected by the rainfall also. So this is one of the very new class of observations that is recently come up in the last 5 years only. Another is the laser-based wind profilers. You can see these depend upon the scattered signal and the Doppler shifts of those wavelengths and those signals. And based on that, they measure the vertical profile of the wind. So this is the first time, I think 2-3 years back, this is the first time this kind of sensor has been launched. And a lot of studies going on that what is the impact of this kind of measurements on the weather forecasting. But this so these basically track the aerosols and the air molecules and their shifts. And based on their Doppler shift, they guess that what is the wind speed and the wind direction. This is a wonderful observation that has come very recently. Now, by saying all these things, let us see how much data is coming from satellites. So you can see that this is a huge amount of, I think this number is coming in the millions. The millions of the points are coming every 6 hours from the satellites, and they are ingested into the model through data assimilation. So that is one of the single use of this observation is to get into the data assimilation stream, into the model, and then improve the weather forecasting by that. So you can see that these are the observations, and what you can see, these curved lines are basically the satellite paths. So they are coming from the polar orbiting satellites, and they provide you the large number of measurements over that region. And these are the measurements which are coming from the satellite for the wind. So in whole, a large number of measurements are coming from satellite observations, and they are ingested into the models, and they are directly helping the weather forecasting. So how satellite observations basically help NWP system? So they help in 2-3 ways. First of all, they provide the better initial condition for the model. As I told you in the very beginning, that the initial conditions are very important. And second thing, they are useful for the model validation. So when the models we predict something, we have to validate it. How good was our model forecast? So these model forecasts are validated against these satellite observations because they provide a very wide coverage of the observations. So they are very good for the validation also. And they also improve our understanding of the physical process, like how we predict the clouds, how we predict the rain, etc. So they are very good in predicting they are helpful in improving the understanding of those physical processes. Now, how observation is used? What is the data assimilation actually? What is data assimilation? So I'll give you a very brief overview of what is data assimilation. Actually, data assimilation is a very important branch of the weather forecasting, and very important in the today's scenario. As I told you that observations are coming from very different sources. They are coming from satellite, they are coming from ground-based systems. They have their own error and their own accuracy, own uncertainty. So how we combine all these observations, knowing their errors and their uncertainties, and how we combine in a very effective manner so that our forecasts ultimately improve. So that itself is a big science actually. And then there's a lot of research is going on in the data assimilation. So what happens that no matter how accurate observations you give, in this graph, I have shown you 2 lines. One is the blue line and one is the red line. So red line is basically the forecast, and the blue line is the forecast, and the red line is actually where is the actual weather is going on. So you know that after some time, no matter how good is your model and how good are your observations, after some time, these forecasts will definitely deviate from the observation. It will, after 6 hours, it will start deviating. So you have to again correct it. For example, if you are driving a car, so you just take a good look at the road and you start driving a car, then what happens is that you close your eyes and then start driving a car, then you will not be able to drive for more than a few meters. Because after some time, your memory will not be so accurate to exactly remember that where there was a tree or where there was a pole. So you have to open your eyes again, 2 or 3 times, and then you will be able to drive. So this is fit the new information, and again you can close your eyes for another 5 seconds. This is the same thing that happens with the models also. So models don't remember for very long that what they have observed before sometimes. So they have to be fed with the observations, new observations every 6 hour time. So you know that, for example, these are the observations. So this is what we want to know. We want to create a state, initial state for the model. So we have to get the initial condition for every grid point. Okay. But observations are not there in every grid point. So neither satellite nor the conventional observations are available at every grid point. Okay. So what we do, we use this forecast from the previous run as one source of information. Now I give you this example. For example, we want to know the precise measurement of time. Now your time information is coming from different sources. For example, you have a Rolex watch or Omega watch. This is a mechanical watch, for example, but even though it is a very expensive, but their uncertainty or accuracy is 4 to 5 seconds per day. Okay, so we know that it can be wrong by 4 to 5 seconds per day. Now you get a digital watch which is very cheap, but its uncertainty is error is very less. It gives you accuracy of approximately 0.5 seconds per day. Then there is a very expensive atomic watch, and nowadays people are making atomic clock for the room, which you can keep in your room, and that is $2.7 million watch. Its accuracy is 10 to the power 9 seconds per day. It means in 100 million years you will make an error of 1 second. So you are having information from these sources. So which source you will rely most? So obviously we will rely the source which is having the least error. And this is very important to know. So what is the difference? Now, it is very important to know the concept of the error versus uncertainty. What is error and what is uncertainty? It is very important to know about that. So error is something that we make at any given point of time. Next time we make a different kind of error. So one error, next time we take the same measurement, the error will not be the same. Error will be different. So error keeps changing. So this in this small animation, suppose this is error is 3. It goes there. Next time if I make the same measurement again, so that error may be on the negative side. So this error is projected here. So if I repeat this measurement many times, so I get many realizations of this error. Sometimes error is there. Most of the times the error will be 0. Sorry, this is a very long animation, so sorry for that. sorry. Actually, I should have made it fast, but so ultimately these errors will keep on accumulating. So at some place, so as in the vertical we are going, it means that many numbers of times these errors have repeated. So small errors come very frequent, large errors come very rarely. So we cannot make a very big error very frequently. So most of the times, less errors, smaller errors are coming more frequently than the large errors. So ultimately, when I this is too slow actually. So sorry for that. Very slow. So anyway, I want to say that the errors have a distribution. So small errors are more in number, large errors are less in number, and ultimately, sorry for this. So they follow a Gaussian distribution. Again, it is starting from the same point. How can I skip actually? Anyway. Took so much time. Okay. So means different sources have a different errors actually. So if I see the variance, so that's called the variance. So error is one time, and if I repeat this experiment infinite number of times, I get a distribution of errors. This distribution is normally a Gaussian distribution, and the width of this Gaussian distribution is called the variance of the observation. So if you have the larger variance, that means the observation is less accurate. And if you have a very small variance, the observation is very accurate. In this example, mechanical clock has a large variance, digital clock has a slightly less variance, and the atomic clock has a very, very small variance. So when we take an optimum estimation, we actually weight them in the inverse proportion to their variances. So it means the weight of this observation, the blue observation will be less, digital will be medium, and the atomic clock will have a very large weight. So when I take a optimum estimation, so the weight, I take the weighted mean and take the and divide by the sum of the weights. So you can see the most accurate observation takes the highest weight. So that is how optimum estimation is done. And based on that, this is the basis of the 3D VAR and the optimum interpolation. In 3D VAR, we also use an observation operator, which I'm not going to talk about you here. So that's how we combine different sources of information to get a correct estimation of the initial state of the weather forecasting. So satellite has one error, radio sonde has another error, other source of observations have another error, and we combine them by seeing at their error and get the optimum estimation of the initial state. Now, there is another method that is called the 4D variational assimilation, which basically tracks the entire trajectory of the model and then goes back and to see what is the best initial state where it can, which can give this kind of trajectory. So this is a very different kind of, and another kind of forecasting method is called the ensemble Kalman filter. And this is a very, very interesting method of combining the observations. And I'll tell you a very good example, very simple and very interesting example of this Kalman filter. Many of you may not be knowing that you are using Kalman filter on almost everyday basis, or maybe once in a month or once in a week basis. And I'll tell you how you are using it. For example, you start from your home to pick up your guest from airport. So you want to go to airport, okay? So you take up your mobile, you go to the Google map, and then you see how much time it may take to reach the airport. So mostly it is nowadays everybody uses this kind of app, and they tell you, so this app will tell you immediately that time to destination is 23 minutes. So where this 23 minutes is coming actually from? So it certainly has some uncertainty into that. So Google will not tell you that what is the uncertainty. They will just tell you 23 minutes. They will not know, Google does not know what car you are driving. They don't know how slow or how fast you drive. So they use many sources of information in their model actually. For example, the model of the car, there are lots of uncertainty in the model of the car, model of the driver, road conditions, country, time of the day, time of the week. On the Sunday, this time will be much less. On the other weekdays and around morning 10 o'clock, this may take very long time because there is the office time. Evening time, in the noon time, it may take much less time. So all these things are there embedded into this model, and based on this model, it tells you that you will reach in 23 minutes. But there is uncertainty in that because 23 minutes is not precise. You will not exactly at 25 minutes and 59 seconds you will reach there. It is not like that. 23 minutes plus minus 2 minutes or 3 minutes. That is uncertainty that they don't tell you. So suppose you imagine, so this is the Gaussian graph that they are imagining, and they are assigning some amount of uncertainty with this measurement or this assessment or this prediction of the time. So this prediction of time is same as the weather prediction. They are predicting the time to reach, and this is a more practical example of that. Now suppose suddenly you reach a point where some people are dancing and there is a marriage party going on, and then because of that there's a traffic jam. Okay, so what happens that this kind of situation, this Google has not imagined because this is happening suddenly. So what it will do, it will not imagine or not take its own previous variance. What it will do, it will change its variance. So it will change the variance according to the situation. So when you change the error characteristics of your model based on the situation that you are coming through, then and you reforecast your system, reforecast it. So every time, so every given time step, every few hour time step, you take that what is the new error in the system and you predict the error. And based on the prediction, you issue a new forecast. So this is the new forecast. So it has recalculated this whole thing depending upon the new variance And then it has calculated that now the time to destination is 26 minutes. So this is the very practical example. This algorithm actually use the Kalman filter, and they use the Kalman filter in continuously correcting their predictions. So they every time they measure what is their guess, what was their prediction, how much they have gone wrong in this prediction, and how to correct this prediction for the future. And this is the basics of the Kalman filter based predictions, where you constantly keep and watch on the errors. So for example, if I'm taking the satellite observation of the wind, so normal days the wind error is maybe 2 meter per second, okay? But some day when there's a big stormy weather and a lot of big storms are coming, the error of the measurement of winds can be 5 meter per second. So that day the wind error was very high. So model will know that today I have made a big error in this. So maybe in the next 1 hour also this kind of error can persist. So this it forecasts the error also, and then it weights the different observations accordingly. So that is a quite advanced type of the data assimilation system, which takes into account this kind of dynamic error characterization. And that is the beauty of the Kalman filter. And that is why it is a very popular mode of data assimilation into the models these days. And then people are going to the hybrid data assimilation also. So the error propagation, the error characterization, they do by the Kalman filter. Analysis step, they do by the 3D, 4D. So because this is cheaper, this is slightly less expensive in time and more accurate, and it combines the strength of the variation and sequential methods, and it provides the hybrid method. So this is the basis which combines the variation and the ensemble Kalman filter methods. Variation does not propagate, does not forecast the errors. Kalman filter forecasts the error and uses it. And when you combine the characteristics of both of them, it is, I think, cheaper in computation, and is quite as effective as the full length Kalman filter method. So this is one of the methods for the data assimilation into the models. Then what is the impact of the satellite observations actually? So this is the picture which tells you that how much impact the satellite observations make. So how we know that how much impact each satellite observation is making? The best way is to know that you remove that satellite observation from the system, and then you know how your forecast is degraded. So that is the best way to know. In the same way, in the practical life also, how we know the value of a person. So you means cut down your contact from a person, and then you find out that how much difference it is making in your office or in your life or whatever it is. Then you know that what is the value or what is the importance of that person. So, so if there is no difference, their life is going as smooth, that it means that person was not important for you. If it is making a lot of difference in your life and day-to-day life, it means that person was very important for your organization. Or that is how, in the same logic, we calculate the importance of any observation. So you can see in this that if you don't apply satellite observation, that error will grow very high even in the northern hemisphere. In southern hemisphere, definitely it will grow. That is, you can see the second graph. In the southern hemisphere, basically the forecast will go completely haywire if you don't use the satellite observations. But even in the northern hemisphere, they make a lot of difference and significant difference. And this is the picture which shows that which satellite observation is making the maximum impact. So if you, the first picture on the left-hand side is telling you, the top picture is telling you what is the impact of radio sonde observations. Radio sonde tops the list from the global, that is the global mean. The first picture is the global mean. In the global average scale, the radio sonde, that is the conventional old style radio sonde observations, make the maximum impact. Then this is followed by the satellite observations. And there are different kinds of satellite observations like the GOES, buoys, aircraft. So the second number is the geostationary satellite winds. In the northern hemisphere also, radio sonde make a lot of difference. In the tropics, the geostationary winds actually make a lot of difference. So winds is the most important observation in the tropics. Radio sonde comes second, aircraft third, AMSU, which gives the temperature and humidity profiles. This comes fourth, AMTS, etc. In the southern hemisphere, AMSU makes a lot of the maximum impact, followed by the geostationary wind, AMTS, ARC, all these observations. And this is monitored every month or every fixed interval of time. So every operational agency keeps a track of this chart. They want to know that suppose there is a new observation has come. a new satellite has been launched and there is a new sensor, for example, like the GPS RO or the GPS reflectometer, or maybe the like the wind profiler. So people want to know that what this new observation, how much impact it is making, what is the value of this observation, whether it is making any impact or not. So in this list, actually, I told in the beginning or maybe somewhere in the middle that GPS RO is making a lot of impact, but in this list they are not featuring anywhere. They are featuring at the 1, 2, 3, 4, maybe 7th, 8th place. Why it is so? If it is so important parameter, then why it is coming at the 8th place? It is coming at the 8th place because the number of observations are very few. There are not many occultations, not many times that it happens that the GPS sends a signal and it is intercepted by some receiving satellite. So the number of observations are less. But if I take the observations, the impact per observation, the impact is very, very high. So if somebody launches 100 satellites or 200 satellites of the GPS RO, I think easily this observation will come at the number 1 or number 2. So it has a lot of impact of this radio sound observation, or sorry, GPS RO observations has a very big impact on the forecasting. And the recent advances, I think there is a huge impact after 90s or 2000s with what is we call the satellite era. You can see the graph. This is the improvement graph. How the weather forecasting has improved. You can see the slope of this graph suddenly changed. It became very high, I mean, it's quite significantly high after satellites have come in 1990s or 2000s, or maybe 90s, 80s afterwards. The slope of this skill and the improvement has increased very drastically. And nowadays, the forecast error of the 5 days is same as the forecast error of maybe 2 days. So nowadays in the forecast error of 5 day long forecast error is much less compared to what was the accuracy of 2-day forecast 10 years back or 20, 30 years back. Today's 5-day forecast is much more skillful compared to the 1 or 2-day forecast 10 days back. So this shows that how much impact this satellite observations have made, and the life will be very difficult without satellite observations, and the models will not be able to operate properly. So just I'll add a few lines that today the weather forecasting models used about 95% of their data, whatever data they want, it is coming from satellites. But actually, this is only 5% of all the data that satellites produce. So there are many practical reasons for that. You cannot put all the satellite data into the models. It is very difficult because the number of observations increase, and then their matrix becomes very, very huge and very difficult to invert that matrix, to play with that matrix and to handle that kind of matrix. So this operational agencies, what they do the thinning of the observations. So they reduce the number of observations purposely, because they cannot handle so many millions of observations. But someday probably some good forecasting methods will come which can handle this kind of observations, because the techniques are being improved day by day. And we are making a lot of progress in data assimilation, numerics, analytics, data sciences. Data science also we are making a lot of progress, and artificial intelligence. So many new methods are coming, and probably that day is not very far when we will be able to use a large amount of the satellite observations for the huge improvement in the weather forecasting. With these lines, I thank all of you for listening to my talk carefully and with a lot of patience. Thank you very much.
Thank you very much, sir. Now it's open for questions.
So actually,
can I ask one question?
Yeah.
See, I just wanted to know, has somebody made an exercise that if the forecasting was done on 30-kilometer grid and was compared with a 9-kilometer grid, that our old method of extrapolation between the 30-kilometer grid, how far it is from the modern day 9-kilometer grid data?
You want to say that how accurate 9-kilometer forecast is?
Yeah, compared to the extrapolation from the 30-kilometer grid. You see, I'm saying the old days we had a 30-kilometer data.
Yeah. No,
now you have a big computer, too much data. You can always do 9-kilometer, 1 kilometer, 2 kilometer. Question is, where do you stop?
Right. Actually, over the oceans, I think it will not make much difference between the 9 kilometer and 30 kilometer because the surface is very homogeneous and smooth. But over the land, it can make a huge difference between 9 kilometer forecast and 30 kilometer forecast because what high resolution models are gaining is from the land surface heterogeneity. So you have a lot of heterogeneity in terms of the land surface used. You have somewhere city, after 5 kilometers, you have a river. After 5 kilometers, you have a road, you have a forest, you have a vegetation. All these things are affecting the forecast in a different way, and the high resolution models are able to take care of that. They can really calculate all this physics and the processes at that scale. And that is why, and they can take care of frictions because in 30 kilometer grid, the city, forest, everything comes in the same grid. But in 9 kilometer grid, everything is separate. And that is how they're able to produce a better forecast of the temperature, surface temperature, winds, humidity, and to some extent rainfall also. But I'm not sure about that.
Thank you.
So,
any other question?
Yeah.
Yeah, any other question? So,
Yeah. This is Chandrasekhar.
Okay.
Yeah. So you said rightly that observation is very, very important.
Yes.
Now we all know that observations of the ocean are very, very scarce compared to the observations of the atmosphere, right? So how does one explain that the ENSO forecast is much better than the Indian monsoon forecast?
Oh, right. ENSO forecast is better because of many factors. For example, ENSO is a purely tropical phenomena. And compared to the monsoon covers some part of the subtropics also, and particularly in the other northern hemisphere, northern parts of the monsoon region, we are dealing with extratropical forcings also, which are having lesser predictability on the day-to-day times, on the seasonal to sub-seasonal time scale. So these tropical systems are predictability of the seasonal forecasting is much better because the forcing of the winds, etc. Because this El Nino is El Nino forcing, the main forcing for El Nino is basically winds. And our observations of the winds are quite good from the satellites. Like the spectrometer satellites, or maybe there are a number of satellites which give you wind observations, like the SSMI, microgradometers, and then GPS reflectometer. Of course, they are coming recently, but previously there are many spectrometers and the microwave radiometers, which can give you the wind information. So they can, if you assimilate all this observation into the model, like the ocean models, they can pick up this kind of things quite quickly, and they can provide a seasonal scale forecasting from these observations.
Okay. So it was a very interesting thing which you told, that the radio Sunday has the highest impact.
Right.
So despite the land covering only about 30% of the surface area of the planet Earth,
right.
And then we also have relatively not very good density of radio sound stations, especially over the entire land area. So would it not be a good idea to actually spend more money on radio sound wherever it's possible over land?
Absolutely. It is your point is extremely valid. And radio sound has a deep impact because they provide a very high resolution vertical structure of the atmosphere, which is required. And they provide a good horizontal resolution also. So even though they drift a lot, actually, once the radio sound balloon goes up, it drifts by as much as maybe 100 kilometers or maybe sometimes even more, depending upon the jet or the location of the balloon. But despite that, they provide you the fantastic picture of the vertical atmosphere. Without that, it is very difficult to do the long-term, maybe 5 to 6 or 7, 8 days forecasting of the weather.
So another observation I found was over tropics, the importance of radio sound becomes only second important compared with the coast wind.
Yes.
So while in the global domain, it's much more important. So because radio sound also gives you wind, which is important over tropics.
Right.
Why it is pushed to the second important impact factor, I'm still not able to like.
Yeah, the answer to this question, answer to your second question actually lies in your first question itself, because the number of radio sound is less.
Okay.
So we are getting many, I think millions of winds, or maybe at least hundreds of thousands of the wind vectors from the geostationary satellites every 15 minutes of time. While we launch, so that is why this geostationary satellite winds make much more impact over the tropics. And second thing, that in the tropics, if you see from the point of view of scale analysis,
yeah,
the winds are more important compared to the pressure.
Yeah.
So basically, the winds drive the pressure in the tropics, while in the extratropics, the pressure drives the winds because of the large Coriolis force. So that is why the winds give the primary impact, which is consistent with our theory, which we have read in the Halton's book.
Yeah, the last question is, in southern hemisphere, without the satellite observations getting ingested, the error is much higher compared with the northern hemisphere error. So the improvement in the forecast is much more dominant over southern hemisphere if you don't include satellite observations.
Right.
So except for the fact that you have a larger percentage of sea over southern hemisphere, what is the other difference which causes the critical importance of satellite observations in southern hemisphere?
Critical importance is the lack of conventional observations. So why we get a better impact of the radio sonde in the northern hemisphere? Because the radio sonde is mostly situated in the land over the northern hemisphere. Okay. So it is because of the lack of observations over that region in the southern hemisphere that satellite get dominance. Suppose we have so many like radio sonde observations in the southern hemisphere, the satellite will immediately come to the second place.
Okay. Thank you.
Yeah.
I just wanted to ask Dr. Kishtawal whether some of your transparencies are available on PDF format somewhere where one can get them.
I can send you the entire PDF, entire my presentation. If you give me the.
Well, if you give it to Punaram, he can send it across to me.
Sure. I think I'll give it to him and he can distribute it to you.
Yeah, he knows my.
I hope that you have liked my presentation.
No. I enjoyed it, but mine was a very basic question. The question is that at what point one should stop thinking of the resolution, because one has a tendency, let us grow bigger and bigger, have more data. I can 1 kilometer and so on.
Actually,
that is okay when
sir,
you want to do.
Sir, let me tell you one thing, that with every advancement in the forecasting, there are new customers or the clients or the users are added to the list of the weather forecasting who use weather forecast. For example, if we start providing the forecast at 9 kilometers, suddenly the list of the users increase 100 times. Now, if we come to the 1 kilometer, it will increase by another 100 times. And then if we come to maybe 10 meters, it will be, I think, nobody knows that how much it can grow, because people want to know that how much it will rain over my roof in my farm, how much it will rain on my farm. So every farmer who is now agitating, they will be now go back to their home and they will start using this forecast.
I see. No,
yeah, just one more thought which came to me. So it looks like we don't really have to worry about that we don't have a perfect theory for turbulent flow.
Excuse me?
Yeah. That's because the observation take care of that.
So in a sense that we don't really have to unduly worry about the fact that we don't have a theory for the turbulent fluid flow. We still, it's all said and done, the theory is not perfect. So, it appears to me that at some point of time, all these observations, all this sophisticated computer models and all can really, to a great extent can, like, what I should say, fill the shortfall of all this, because we have lots of issues with the physics of the models, right?
Right.
Yeah, but
that
the way you are telling that every 20 years we are able to get today a 5-day forecast is as good as what it was 20 years back, which was the skill of a 1-day forecast. So if one would have to extrapolate over the next 20, 30 years with the sort of computing facilities we'll have, the sort of, ensemble methods which will come into play, the sort of number of ensembles which we will deal with it. So all these underlying physics deficiencies will just go away. Or we'll get a point where this will, there will be no further improvement in the skill.
Shall I answer this question?
Yes.
Okay. Yeah, definitely there is a limit. There is a theoretical limit. We cannot go beyond 15 days or maybe 2 weeks. After that, it will be definitely we'll facing a lot of more and more challenges. More and more complexity will add to the more errors actually. And then they will be becoming a challenge in itself to handle so much data and to handle the non-linearity that is coming from this data and so much interaction. So that is why there is a theoretical limit. In the very beginning, I told you about the chaos and how we cannot overcome this chaos for a quite long time. Maybe I do not know whether it is a theoretical limit of the nature. So we cannot overcome this despite big computers and despite big models, artificial intelligence, so much data. It will be very difficult to beat chaos. It is my personal view. Actually, it is my personal view, but chaos becomes very important after a certain time.
No,
so we cannot go up to 30 days or 40 days, no matter how much progress we can do.
No, essentially, if you look at it, chaotic behavior is due to the essential nonlinearity. Now, if you're using, like, for example, semi-Lagrangian schemes, then you need not have to deal with the nonlinear terms, right?
Right. But so then
you have a workaround, a solution to take care of the nonlinear terms that arise in your equations. Then possibly the importance of chaotic situations also become less.
Right, but unfortunately, you cannot handle everything by Lagrangian way. For example, the rainfall processes, the parameterization, how many rain droplets become a raindrop, how the convection takes place, how the convection triggers. Those kinds do not come under the domain of Lagrangian framework. So those things we have to still deal with the parameterization and then, or maybe observations. And then I think it goes to molecular level, because once we go to the rainfall process, it is starting from a molecular scale and then going back to we cannot handle that much numbers actually.
Dr. Kishtawal,
yes, sir.
Can I ask a question?
Sure, absolutely.
You see, the main purpose of forecast, at least in the tropics, to know the rainfall. Okay, other parameters notwithstanding, the main forecast parameter is rainfall.
Right.
And there is no, as such, a forecast of rainfall. It is inferred from the various other equations. Say, for example, that is when the humidity becomes 100%, etc. It's basically parameterization. So it all boils down to parameterization to forecast rainfall. Is there a possibility of writing out an equation for rainfall? Is there a possibility? I mean, as such, we don't see, because it is so much varying in space and time, so much. But is there a possibility? Say, for example, the liquid water, for example, is much more smoother than the rain in space and time. So can we find another parameter which is equivalent to rainfall, as I said, cloudiness or liquid drops? Can we formulate an equation which may be the answer to many of the questions that we asked today?
Yeah, Dr. Narayan, thank you. And it is a very interesting question, and it is a very question. Actually, the answer can be yes or no. So, yes means, like any process in the nature, the rainfall we should be able to model the rainfall process also. Like anything we are able to model, like the Newton's law for motion and the thermodynamics, etc. But unfortunately, in the rainfall, there are lots of things which are working like an on-off switch. They are like a triggers. For example, under a certain humidity threshold, it triggers. It happens, and just below that, for example, humidity at 100%, it happens. 99% does not happen. So those kind of triggers and switches are there, which we have to handle through a different approach than the equations, because then the equations becomes because that's called the non-continuous equation. So there is a lot of discontinuity in the rainfall equation, and you can see the rainfall parameter and the rainfall also. It is a discontinuous parameter, unlike your temperature and the wind and moisture. So rainfall is a discontinuous parameter, both in time and space. It is happening. It happens for a few days, and then it does not happen for many days. So those kind of things will be difficult to handle. I don't say that it is impossible to handle, but will be difficult, and we have to take care of those kind of on-off things, like switches we have to handle, like the triggers we have to handle properly. We have to find a way, define a function, like a step functions or maybe step functions, which can act as on-off, and which we can incorporate into a model. I think this is my understanding about your question.
Thank you.
So, any other questions from participants?
Yeah, just one question. So, like for example, this thermodynamic energy equation, we have this diabatic heating rate, now which we don't measure at all in the atmosphere, right?
Yeah.
That's such an important term. So the question is, are we not really? Don't we ever think that we can handle this? We can measure this and put it in the equations?
Yeah,
rather
actually,
than the way we. Yeah.
Right. There are some attempts are going on in this direction from satellite measurements.
Yeah.
Some attempts are going on, and that CubeSat is one such effort. So the basic, if you see the basic document of this CubeSat concept, which is being basically led by the NASA team. Dr. Jihad Haddad is the team leader of that. So if you see their concept paper, they talk about, they want to measure this kind of changes in the this thing by the very frequent measurements. So if you have, for example, 100 or 200 CubeSats, small 5 kilogram satellites, which can measure the thermal structure of the atmosphere with some small sensors, and every 5 minutes or every 10 minutes, a new satellite comes over there, which can measure these quantities more precisely, then probably we can measure the d temperature by dt time, that term more precisely. Okay. Yeah. So this that is a one single measurement efforts I am aware of.
Okay.
So there is one question from students, sir.
Yeah.
In the chat box. Can I read, or you can read, sir, at your end?
No, actually, I cannot read because I am in my.
Okay, fine. I'll read it. Or Sunil, can you?
Yeah, if you can help me, that will be great.
Okay. Sunil, is it possible for you to read, or should I read?
No, I cannot read.
No, I'm asking.
I can read.
Okay.
I can read basically, but
okay,
if my mic is working.
Yeah. Okay.
Properly. My first question is: can we scan the entire globe with a geostationary satellite? Yes.
Okay. And then what is your second question?
And are they necessary to maintain the orbital distance, which is 36 kilometer orbital distance from the
36,000 kilometers.
36,000.
Yeah. Actually, you cannot scan the. Yeah. Okay, Sunil. You cannot scan the entire Earth from one satellite because one satellite, at the most, it covers only 1/3 of the globe. So you need minimum 3 satellites. But in the three satellites will give you, on the edges, they will give you very poor resolution. On the center, they will give you very good resolution, but at the edges, they will give you the very coarse resolution, and the data will not be very much useful there. So even 3 satellites are not enough. Probably you need 6, 7 satellites to thoroughly scan the globe. And that is done, actually. That is already done. There are, as one of my slides, I showed that there are 2 satellites by US, I think 2 or 3 satellites from USA. There are 2 satellites from Japan. There are 2 satellites from India. There are 2 or 3 satellites from Europe and Korea, China, Russia. So there are, I think, more than 10 geostationary satellites right now, which are scanning the entire globe. And they are providing the wind information. And these wind informations, these centers like IMD in India, it derives, and they immediately transmit to the GTS, that's called the Global Telecommunication Network, telecommunication system. And it immediately gets available to everywhere throughout the globe. So whatever INSAT is measuring in India, it becomes available to the entire global community in the America or Japan, etc., within half an hour. Or maybe not even half an hour, within a fraction of a second. And the second thing is, it is very important to maintain the distance of 36,000 kilometers, because if you don't maintain this, then satellite will have a different evolving speed, and it will, after some time, it will lose that 24-hour time period. So it has to be very precisely maintained. So if it goes beyond that orbital point, or its orbital position, it has to be pushed back to that its original location, and for that they use some kind of fuel. It is like a can, like a spray can, and it pushes the can, and the satellite moves in the opposite direction. So like that, they control the satellite almost on a regular basis.
And so, sir, are they orbiting on the 0-degree inclination with respect to Earth?
Yes, absolutely.
So,
it is in all geostationary satellites only. Only geostationary satellites are orbiting on the 0 degree. Other satellites are orbiting around the globe.
Okay.
They are polar orbiting satellite. Actually, I skipped that because the time was short and I had many slides. So you can go to internet and read about polar orbiting satellites. So they are a different type of satellites which are at a much closer distance, like 800, 700 kilometers from Earth. They are not like 36,000 kilometers. And there are many satellites like in the polar orbit. So they go from north to south. They don't circle on the equator. They go from north to south. That's why they are called polar satellites.
Okay, sir.
Okay.
And my last question was, what the data, which the data we can get from remote sensing. So how these images can be differentiate how the images of, how we can read those images which we can get satellite through remote sensing.
How you can read those images?
Yes, sir. What information we can collect with this?
Oh, okay. Actually, nowadays, different centers, operational centers like ISRO and IMD and Europe, America, etc., they are collecting their satellite observation. They are processing it. It is not a direct satellite observation. They process it. They process. There are a lot of processing is involved. And after that, the final product, that is called the level 1 product or level 2 product, they clean the data. They look for the possible mistakes in that. Then they give it to user. And these data is available mostly in the NetCDF format or the HDF5 format, which you can read easily by any software. If you have Python or any other language, you can read it very, very easily.
Yes.
So,
sorry to again ask a late question. See, Dr. Kishtawal, you have emphasized on observations.
Right.
Does it mean, of course, obviously you don't mean, if you have to weigh between the theory and observations, So what type of weight will you assign?
Theory, actually theory means basically the model.
Yeah, yeah.
The model background is coming from theory only.
Yes.
So you can assume that the model background is a representation of theory.
Yes.
Because many places observations are not available. So this at many places like deserts and the southern hemisphere, this theory has much more weightage compared to the observation, because you don't have anything else coming there. And this a very good paper and very good news item. I remember even from 2001. In 2001 itself, the models were so advanced that one satellite actually missed some sensor actually failed, and or the operational center were not receiving the data for some time, maybe some few hours. So there was no data, no satellite data. So they were providing the forecast based on entirely upon the model forecasts. So there was no observation at that time. But when the satellite data started coming, and then they processed the old data, they compared, they found that the models were able to reproduce the satellite data very, very accurately. So nowadays, actually, and the second answer to this question is that people have done this experiment, Dr. Narayan. People have done this experiment recently. So what they did, they have tried to answer this question: what is more important, model is more important or observation is more important? So they have tried to answer this question in the following way. So what they did, they took a new version of the model and they put all old observation into that. Okay. So they put the observation of 2000 or 2001, 2002. Okay. And then they try to predict. Then on the other hand, they took an old model and they put the very latest observations into that. Okay. So there are two experiments people have done. What they found is that the model, the new model with the old observations was much better than the old model with the new observations. So it means the model has its own strength, which basically is not less than the strength, which is not less than the importance of the observations. अभी चली रहा है हाँ चल रहा है please go ahead, please go.
Okay. So,
Dr. Narayan.
Yes.
So, did you listen my answer?
Yeah.
Is it okay?
Yeah. I mean, yes, it is one point of view. I have always been wondering about this. I mean, of course, there is no one clear-cut answer for any of these questions. So it is your point of view I wanted to know.
Yeah. So there was an experiment, and I told you about that experiment that
Yes.
that you heard, because my network went for a short time.
No. I could hear.
Okay. Thank you.
So thank you very much once again, sir, for this excellent talk. And I'm very much sure that all participants might have definitely, I hope all participants might have definitely benefited from this talk. And on behalf of IST and all participants, I take this opportunity to thank you for this wonderful talk. And I also thank all the participants for their active participation. So thank you very much, sir.
Thank you so much, Dr. Sinha, Dr. Chandrasekhar.
Yeah, thanks a lot. Thanks.